Welcome to another Zeppelin episode. Exactly 100 years after its completion, we want to take a detailed look at the design of Germany's first big Zeppelin after the First World War, the LZ126. To better understand the construction of this very special and successful Zeppelin, I was designing it in CATIA, and we will have a closer look at this throughout the video. As we discovered in the last episode, Britain and France demanded a limit for the maximum size of this new German Zeppelin for the USA. So instead of 100,000 cubic meters, it could only have a gas volume of 70,000 cubic meters, so that it's not bigger than French and British Zeppelins. Consequently, for the hangar the Germans still had in Friedrichshafen, the ship was 200 meters long, and its rings had the largest diameter of 27.64 meters. Including cabin, it was 31 meters high. So let's take a closer look at these rings first. First of all, these rings are built with beams, and these beams are profiled aluminium elements which are riveted together. The Zeppelin company had their own design and test department for these beams, and they developed these structures a lot further over the years. The first Zeppelin had very simple L and T elements. LZ2 and 3 had tubes in their beams and a triangular structure. A huge innovation from LZ7 onwards was the introduction of crimped profiles. They were very light, gave a lot of stability, and were easy to manufacture. This, by the way, was an idea of a man called Claude Dornier, a new engineer at Zeppelin. If you want to know more about Claude Dornier and his path to his own airplane company, check out my video series about him below. A new design which was first used in the LZ126 were now beams with a box profile for heavily stressed areas like the rudders. At Zeppelin, they analyzed their designs in great detail. First, they inspected the base material looking for cavities. They material tested their supplied aluminium, then crimp tested it and also checked the material for changing properties through aging, corrosion, heat and cold treatment. After assembly of a beam, they tested it for bending, also with combined loads. As an example, this is a 2.6 meter long beam of the LZ126, which could withstand a vertical load of 7,043 kg before it kinked. And this beam only had a weight of 1.3 kg. So it could withstand the same loads as beams which are built with pipes, but it's a lot lighter and cheaper. Also, for the Zeppelin company it was very important to use beams which just bend but keep the connection instead of suddenly failing and breaking apart. Also, while failing, the structures shouldn't create sharp edges to avoid puncturing the gas cells. That's why all components of the beam have rounded edges. A ring of the Zeppelin LZ126 was a 24-edge profile of beams. The two lower pairs were extended, which created a reinforced structure at the bottom of the ring. The large triangle in the middle is the catwalk through the Zeppelin. And this is a support ring. We will see what that means in a minute. A main ring is a bit more complex and had a double beam structure for reinforcement, here yellow. At the connection points between the double beams, the reinforcement cables were connected. So this gave them a very light and rigid structure. The gas bags were sitting between the main rings. The gap between main rings was 15 meters at the LZ126. Two support rings were positioned between the main rings, so the gap between rings was 5 meters. The LZ126 had a teardrop shape, so the ring's diameter was getting smaller towards front and back, but the main structure stayed the same. So we have a catwalk which runs through the whole ship, from the nose tip to the very back. So you could reach every gas bag while flying and repair it. Also, there were ladders between gas bags so you could go to the top. During war times, they had machine guns on the top. Here it helped to navigate with stars. Left and right of the catwalk are fuel and oil tanks, water ballast bags, compartments for the crew and cargo areas. The heaviest components are positioned at main rings because they can transmit the load into the rest of the structure better. Between main and support rings are many cables and ropes which transmit the lift force of the gas bags into the aluminium structure gently. Another important point to increase reliability of the ship. Between gas bags and skin of the Zeppelin is a certain gap to avoid too much influence from cold rain or hot sun. Each gas bag has two automatic overpressure safety valves with 500 mm diameter. They sit at the bottom of the gas bag to avoid accidentally losing all hydrogen of the bag, and vent into a chimney to the top. At the top, there are additional valves which can be controlled from the cockpit to release hydrogen. And on top of the ship are rearward-facing vents to gently release hydrogen into the surrounding airflow. The skin of the ship uses longitudinal cotton panels to reduce the number of split lines which the surrounding airflow has to cross. In other words, to reduce drag. The thickness of the skin varies depending on the position of the ship. For example, close to the engines and the propeller, it is thicker to protect the gas bags better from potentially flying around ice pieces or other things. The finished skin is then painted with an aluminium powder mixture, which seals the ship against rain, reflects sunlight, and tightens the cotton skin, which again reduces drag. All components are positioned inside the main body. The engines, however, are intentionally positioned outside of the hull to have an air scarf between gas bags and engine car with its ignition system, because this is a hydrogen ship. Later American ships could have the engines inside the hull because they were using helium. The 5 engine cars were positioned at the side and one below the hull, which also carried the rear landing buffer. The cars at the side were positioned in different heights to not interfere with each other. These engine cars could be reached from the catwalk through slide doors and a ladder. The ladder was foldable to reduce drag when not in use. The engines were Maybach VL1 V12 engines with 400 horsepower each, so the ship had 2000 horsepower overall. The VL1 engine was especially designed for the LZ126. Design priorities were reliability, especially under long full throttle runs, high lifetime, and low fuel consumption. It had 33.25 liter capacity, 3 overhead valves, 1 large inlet, and 2 small outlet valves. It had 1 camshaft in the center of the V and 4 carburetors, which were especially designed for airship applications like high altitude. Each engine was started with compressed air to save the weight for the starter. After a start, a 2-step compressor was driven by the engine to fill 2 50-liter bottles with 29 bar. Once the pressure bottles were filled, the compressor switched off and was decoupled. The engines were designed for operating at 1400 RPM, which meant the propeller could be directly fixed to the crankshaft and a gearbox wasn't necessary anymore, so less risk for any reliability issues. Although this is a 4-stroke engine, the rotation could be reversed, for example to brake the Zeppelin for landing. To do that, the camshaft was pushed longitudinally with compressed air. There was another cam for each valve and hence the engine could rotate the other way. The engine car itself was designed in a way that mechanics could easily work on the engine during flight. The car was aerodynamically shaped with a controllable air intake at the front to regulate air for the forward-sitting water radiator. A mechanic stayed at the engine at all times and a shift was 2 to 3 hours. They used wooden 2-blade propellers. The Zeppelin did a lot of research and propeller designs over the years, and after starting with metal propellers, they changed to wooden propellers during World War I, because it allowed them to reach more efficient aerodynamic designs. The LZ126 propeller was a so-called Jahre design, named after Paul Jahre, a young talented Zeppelin engineer who later became a famous car aerodynamicist. LZ126 had an air-cooled exhaust for each bank in the floor of each engine car. The fuel tanks were inside the hull slightly above the engine, so fuel pumps were not necessary. Next to the catwalk were 70 fuel barrels in the normal setup, but this number could be increased to 114 for longer journeys, which extended the range to more than 12,000 kilometers and 110 hours in the air. So the LZ126 could go from Germany to New York and back without a stop. So these 420-liter fuel barrels were hanging next to the catwalk in groups of 3. They were suspended with cables and could be dropped any time. To pump fuel from the large barrels next to the catwalk to the smaller tanks close to the engines, they used propeller-driven pumps. The same barrels were used for oil. Ballast is a big topic in a lighter-than-air vehicle, and so there are two kinds of water ballast reservoirs. There are landing ballast bags, so ballast which can be released very quickly. These are 12 250-liter bags at the very front and very rear of the ship, to quickly change the balance if necessary. The other kind are ballast bags to slowly release water during flight. They hold 1000 liters and have valves and pipes to release water. They hang in pairs next to the catwalk. All ballast bags can be controlled from the cockpit. Officially, the LZ126 had to be a civil airship, which was a requirement from Britain and France because Germany was not allowed to build military airships. And so, the cockpit includes passenger compartments. Also, comfort and safety of the ship had a higher priority than on war Zeppelins before. The cockpit is rigidly connected to the hull of the ship without any air gap, because there is no engine behind the cockpit anymore. So the cockpit can be easily reached from the catwalk with a ladder. Because of the aerodynamic round shape, the floor of the cockpit is slightly higher than the passenger rooms, which you reach through a door and a small stair with 2 steps. The landing buffer is right underneath the cockpit, and you can see the beam structure which makes sure that these forces are transmitted into the Zeppelin's hull without crushing the cockpit. Zeppelins were operated differently to planes. So, in the cockpit, one pilot was responsible for the flight direction, which is the position in the middle, and another pilot was responsible for altitude and trimming. You can see a map of the ship and the control boards for ballast and gas release here. A third officer was responsible for communication with the engine cars, and there was a telephone for different positions in the catwalk. This officer was sitting on the right-hand side at the map table. The rudders were operated by chains and cables which ran through the ship. For emergencies, for example when a cable snapped or got stuck, there was another control board in the stabilizer fin at the back. Clutches allowed to operate rudders in pairs or individually. To adjust the altitude of the ship, there are different options. Hydrogen gas can be released. Ballast can be dropped. But you can also adjust it dynamically by angling the whole ship, so the hull produces lift or downforce. You can do this by using the rudders or change the trimming of the ship by moving ballast, pumping water and fuel to different locations. Behind the cockpit on the left-hand side is the radio station. That is a separate, insulated room with overpressure. The radio station has a communication range of 2,500 kilometers and 500 kilometers for telephone connections. The Zeppelin uses 3 120-meter-long antennas, which have a Zeppelin-shaped weight at the end and can be lowered during flight. The electric system of the LZ126 is very interesting. The standard voltage is 24 volt to keep the weight down, and is with that 4 times higher than on cars in 1924. The ship has a 60 ampere-hours battery, and electricity is generated through a number of wind turbines with 4 and 6 blade propellers. These generators can be moved into position during flight or stored away to reduce drag. So why did the Zeppelin company do this, and why didn't they generate electricity at each engine, which would be much more efficient than through wind turbines? Because with locally positioned wind turbines, they have a short and simple system. They save weight and reliability issues with long cables, and there is less risk of sparks somewhere in the ship. The cockpit even had 2 hybrid generators. So one wind turbine combined a 1200 watt DC generator and a 1500 watt AC generator. The kitchen in the back of the passenger area had its own 110 volt generator. For the 28 crew members, there are crew compartments next to the catwalk. One for the navigators at the front, close to the cockpit, and one in the middle for engine personnel. In these compartments they had a bathroom, a social room and a bedroom. For the passengers they created 5 rooms, and you can see how they were situated between the structural supports. These 5 rooms were like luxury train compartments, so they could comfortably transport 20 passengers, so 4 per room, and in the night they could extend 2 overhead beds, so everyone had a place to sleep. At the back there was a bathroom, a toilet, and opposite is the kitchen with its electric cooker. So the LZ126 was not just important for the Zeppelin company to survive and finally to be allowed to build a Zeppelin again, it was also a masterpiece of engineering with lots of innovations and improvements over previous Zeppelin generations. When it was finished in 1924, it was the largest airship the world had ever seen. Zeppelin boss and captain Hugo Egner himself started with a crew of 27 in October 1924 to Lakehurst near New York. While trimming the ship, they found 2 blind passengers. 2 American journalists were hiding in the back of the ship. Egner couldn't get an insurance for the America trip, and so the Zeppelin company was fully liable for all losses. And remember that the Americans were also not allowed to pay for the ship, so the Zeppelin company financed the build themselves. Within 81 hours they reached Lakehurst, and that was only the second time an airship crossed the Atlantic. After the German LZ126 was called back in 1919, and the British R-34 did the trip a couple of months later. More on this in my other video. The Zeppelin crew was welcomed in New York with a ticker tape parade, and the LZ126, now renamed to ZR3, became the most successful American airship. The Zeppelin and its crew became the best ambassadors for Germany in these difficult times and laid the foundations for future Zeppelin designs. I hope you liked this look back in history, and if you did, please consider to become a B-Sport Club member for more videos like this. See you at the next video.